Hello, everyone, and welcome to our presentation. My name is Janine Donnelly. I am the Manager of Webinars for IBM Systems Magazine, and I will be the moderator for today's event. Today's webinar, How to Get More MIPS Out of Your Z13, is sponsored by IntelliMagic. Our featured speakers today are Brent Phillips and Todd Havicost. Brent has been working with IBM mainframes for over 30 years, starting in operations while in university and later as a systems programmer. He has been working for IntelliMagic for over 11 years and is now responsible for the IntelliMagic business in the Americas region. Todd is a senior ZOS performance and availability consultant at IntelliMagic. Todd's passion and primary area of interest over the course of his 38-year IT career has been ZOS systems performance. Prior to joining IntelliMagic, Todd spent 26 years at USAA in a variety of technical and management roles. Having been impressed as a customer with the visibility IntelliMagic Vision provides into ZOS performance, he now leads IntelliMagic's efforts to reduce MLC software costs for customers. With our introductions complete, Brent, I will turn the presentation over to you.
Great. Thank you very much, Janine. Thank you, everyone, for spending some time with us this afternoon. So the topic today is about CPU optimization, getting more MIPS out of your Z13. It could also be called how to do the same amount of work using significantly fewer MIPS, or how to reduce what you're paying for your mainframe software by millions of dollars per year. We've actually seen double-digit million-dollar reductions at some mid-sized shops. So it's a very interesting topic. We've had a lot of people register. We thank you for your time and think it'll be quite interesting for you. In particular, we're looking at kind of diving into detail on one particular area of MLC reduction, which is processor cache optimization. We do some work in a variety of areas, but this seems to be one of the least explored areas of MLC reduction from our experience so far. And I think it's fair to say that the Z13 is actually more sensitive to processor cache optimization than any previous model. So Todd will do a deep dive into that area. I'm very pleased to have Todd as a part of IntelliMagic. His focus on the mainframe architecture and software cost reduction at his previous employer provides an excellent background for a lot of people to learn from, and I think that'll come clear through the presentation today. I think what he accomplished and what he learned through the process is of great value. So I did want to also mention his presentation at SHARE in March. Some of you may have been able to attend that. The PDF is available out on the web if you want to take a look at that. But he did win a Best Presentation Award for that. And I found it interesting at the session that afterwards I spoke with an IBM Distinguished Engineer that helps mainframe customers optimize their environment. And I asked him how many sites have gone through this kind of optimization that you're aware of. And he said, this is the only site that I know of so far for Todd's previous employer. So I think there's some interesting content here that we have to go through. We've split up the agenda today into 4 different areas. The first one is really covering some assumptions that affect MLC optimization. So I'll cover a couple of slides on that. Then Todd will dig into some slides on the concepts and metrics that we're talking about, switching over to a live demo to kind of show some more data and visibility of what we're talking about. And then at the end of the session today, we'll talk about how you can see some visibility for the opportunities that may exist for your particular workloads on your infrastructure configuration. So Todd and I are both part of a great team of about 70 people at IntelliMagic that are all passionate about solving the problem of how to create better intelligence out of the data so that it improves how you operate your specific application workloads on your specific infrastructure. Not everyone gets immediately why we use the imagery of a lighthouse, but it's an analogy of what we do for the digital infrastructures that run the world today. And if you just imagine what it was like back before the lighthouse era, those responsible for steering the ship when no stars were visible to navigate by, and of course without GPS, you could get into big trouble, right? I mean, all you have is the clouds above and the water below and perhaps a shoreline that you might or might not see or recognize. But if you get too close to that shore, you can hit the rocks under the surface of the water and cause a catastrophic failure. Or if you get too far from the shore, you could veer off course completely and waste some time and money. So the lighthouse, together with the maps about the lighthouse locations and the hidden risks in the waters in that area, I mean, it would give the captain a location-specific knowledge base about how to avoid the dangers and avoid getting off track. So it's really pretty amazing to me that despite how advanced we are in our computing platforms in the world of IT today, we still find out about most problems only after the production systems have already taken a hit. And I think it's really unfair to ask IT staff to manage the infrastructure for maximum efficiency without incurring any performance problems if you don't have good intelligence about where the application workloads are about to run into infrastructure bottlenecks or where the infrastructure is driving some wasted costs. So that's why we like to use the lighthouse as an analogy of what we're trying to help you achieve, giving you specific knowledge that you need to outsmart service disruptions and eliminate wasted cost. So we like to start with a couple of assumptions that are driving the kind of problem about not getting the visibility that you really need. The first one is on the SMF processes that are in use. Most people have spent many, many man-years in reporting on the SMF data in your current processes. So the tendency is to think that it's pretty much about as good as it gets. But from our perspective, the reality is that the greatest potential value that exists in the SMF and RMF data is still unrealized or unutilized. So the mainframe is actually, it's one of the great things about the platform that we work on. It produces the most robust performance and configuration data compared to any other computing platform in your data center. And yet it's still underutilized. I mean, even the smartest people in your shop who know how to build the reports and what the metric means for your particular infrastructure configuration, it just takes too much time to be able to use that data proactively, looking at every RMF interval for how all of the different infrastructure components are handling those workloads in that interval across all of the data centers. It's just completely unfeasible. As a matter of fact, I mean, we are now seeing that sites that have invested decades into their reporting and PDB actually moving away from that infrastructure, that reporting infrastructure, once they see the value of creating dynamic and predictive intelligence out of the data. So another common assumption that we see is that SMF is used for forensics and trending, and those are both true. But most people don't see the value of using the SMF data on the impact for the real-time operations. And probably a lot of you are thinking that's exactly the way I think. But the reality is it can provide visibility that you might term sooner than real-time. So usually when an incident happens, a performance incident, for example, one of your experts will go back and look at the SMF data and try to figure out, do the postmortem and see what happened. That, in fact, can prove in essence that data can be used for predictive value as well if you apply the right expertise of what was really going on to the environment. So that when you combine that context-specific expertise about the infrastructure that's running the workloads, it can, in fact, tell you about the problems that are about to happen and also about inefficiency in the infrastructure that can be costing you money. So if this deep infrastructure expertise can be embedded in the interpretation of the data, then you can get a different result and really mine the data for this additional kind of value that will be much more predictive than what you're used to seeing and really what you can get from your real-time tools as well. And here's another one that's really very much related to what we're talking about today, is a lot of people have been trained for years and years that the processors are so expensive and the costs associated with CPUs on the mainframe are so expensive that you want to run them at 100% to maximize cost efficiency. But the rules have changed, and I hope that's going to become clear. It takes a while for people to change this kind of long-held assumption, but I would go as far as saying that if you're running your Z13 processors at 100%, you're probably significantly overpaying on your monthly MSU-based software bills. So how do you get more out of SMF? This is an area that what we're really talking about, we term it to be availability intelligence. And it's important to say what we're not talking about. I mean, it's not enough just to have easier to generate, prettier graphs and visualizations. A term that you probably ought to be familiar with if you're not already is ITOA, IT Operation Analytics. That's the kind of the name that a general class of new products are going by that will work with machine-generated data and produce new kinds of insights. But the primary method that most of these solutions are using is statistical analysis. In other words, you look at the data, automatically analyzing what anomalies are occurring, what correlations between anomalies or data points are occurring. And that can indeed add some value, but it won't get to this kind of result that we're talking about because you have to have context-specific expertise about the type of infrastructure that you're running. I mean, routing the data off to a platform that doesn't know anything about ZOS or ZOS processors or workload manager or cache optimization or whatever the specific topics are will not get you to the benefit that we're discussing today. So instead, what you really need is to have an understanding of hardware component limitations, for example, built into the automated analysis of the data, especially if you have some performance modeling expertise to know what those particular components are capable of doing. That will give you some early warning capabilities when the peak workloads are starting to approach those limitations. Incorporating best practices specifically for these types of workloads on this particular type of infrastructure is important to arrive at this intelligence concept. And then actually creating new metrics out of the raw data to understand new aspects and angles from it. Because what you're really trying to do is understand, is this good or bad, this chart that I'm looking at about my workloads on my infrastructure? Is it good or is it bad? I mean, if you're just simply dependent upon things like response times being high, I mean, that's a symptom, that's not a root cause. And by the time that goes off, the problem is already there. In the ideal world, you're going to have the visibility about how close to the edge of the capabilities on certain components or infrastructure are your workloads approaching. So that's really what we're talking about with the goal of outsmarting these disruptions, avoiding them, and eliminating inefficiency. So we talk about 4 different areas of benefits. The first one, the prevent, I think some of these words are used by a lot of different vendors, but in my opinion, predictive and prevention is a lot of times hard to substantiate with different types of solutions. So we're really happy to be able to prove some of these predictive capabilities using historical data. If you, that's the nice thing about SMF is that prior to your last incident, you can process the data and look and see what kind of predictive warnings would have been generated before any of the symptoms actually were affected. Most of the ITOA solutions are really focusing on the second pillar of resolving the problems more quickly, which is extremely important to know, when something is happening, what parts of the infrastructure are involved, and of course our approach can add value there as well. We're mostly talking about the optimize pillar in today's webinar about MLC reduction. How do you optimize, particularly the processor complex, to reduce your software costs? In the last pillar there on elevating, really providing your staff, your experts with the most valuable analysis and information or intelligence or knowledge that they need to take the actions and do their job. So a case study before I turn it over to Todd, that I think is quite interesting is what we're going to talk about now. In this particular chart, there's a red line that represents the transactions with the scale to the right in thousands of transactions per day. This is a peak hour, basically. And the blue line on the number of MIPS required to process those transactions. So in this part of the graph, I mean, it's something that most people are historically used to looking at, where they're tracking together pretty well. But something happened here at this point where the blue arrow is, and this is exactly what you don't want to see, probably the kind of thing that is causing IT management to say, okay, we're not going to run any new applications on the mainframe because the software costs are just so high and increasing so fast. Because in this case, the number of MIPS to run the transactions is growing faster than the workloads are growing. So what happened? What caused this particular change at this particular site? Well, they moved the workloads to z13s. So this is exactly what you don't want to see, right? And the reason is really the z13, as most people know by now. I mean, the processor cycle speed is actually slower than the EC12s, but its capacity is higher. And this is really the area that we're talking about, that the processor capacity is more dependent than ever on the effective utilization of the processor cache. So this is not the rest of the story. This is really a beautiful chart right here, because this is a real-world scenario, and having the MIPS required to process these transactions drop down is actually extremely significant from a cost perspective. In this case, it's actually probably closer to 25% reduction in MIPS to handle the same workload. So that translates into millions of dollars per year in savings. We'll get into this, but kind of a rule of thumb is the RNI metric, which is a metric about the efficiency of your processor cache utilization. If you can reduce that number by about 10%, you'll save about 5% of MIPS. So for your MSU-based software bills, that's very significant on what you're paying each month. And most of the sites that we've looked at, the vast majority of them, have some significant opportunities in this area. Okay, so at this point, we're going to move to our first poll. Gerald, if you can launch that. You'll see this on the right-hand side of your screen. So it's, what is the status of your MLC reduction initiatives at your particular site? So there's 4 choices there. If you could move your mouse over and select either not started, we've not yet done significant analysis on MLC reduction opportunities, or if you're at an early stage, we've done some. No, we have some more that can be done. Or C, you're fully engaged. We are fully engaged in identifying and realizing MLC savings. Or D, you're at a mature status where you've already reduced as much as you think is reasonably possible at this point. So go ahead and make a selection. The results should be popping up here. We're going to share it with everybody. I see the poll has ended. Okay, there we go. So 35% say not started, 41% say early stage, 17% fully engaged, and 7% are fully mature. So it looks like there's still a lot of opportunity from most people's perspective. Okay, thank you for doing that. So at this point, I'm going to switch over to Todd, and he'll go through some deeper concepts. You ready, Todd?
All right. Thank you, Brent. Okay, so since effective utilization of processor cache is vitally important for the capacity delivered by Z13 processors, let's discuss some of the key concepts behind optimizing processor cache and key metrics that enable us to measure and improve delivered capacity. So a good metric to start with is cycles per instruction, CPI, and that represents the average number of processor cycles spent per completed business instruction. And conceptually, processor cycles are spent either productively, executing instructions that are present in the level 1 cache in the processor, or unproductively, waiting to stage data that's not present in level 1 cache and thus needs to be staged. So keeping the processor productively busy executing instructions is highly dependent on effective utilization of processor cache. A second key metric that Brent's already referenced, and one that we're going to examine in some detail today, is relative nest intensity, RNI. And this quantifies how deep into the shared processor cache and memory hierarchy, which is called the nest, the processor needs to go to retrieve the data and instructions when they're not present in level 1 cache. Now, this is very important because access time increases significantly for each subsequent level of cache, and thus that results in more waiting by the processor, more unproductive waiting. Now, the formula to calculate RNI is provided by IBM, and it's processor dependent, and it reflects the relative access times for the various levels of cache. This is the formula for Z13 processors, and it reflects the percentages of retrievals from the various levels of processor cache, level 3, level 4 local, level 4 remote, and then finally from memory. Now, IBM defines a threshold value of 1.0 for the RNI metric, above which a workload is considered to place a high demand on cache and thus may not achieve the rated capacity of the Z13 processors. And that was the situation in the case study that Brent spoke about earlier. But no matter what your RNI currently is, reducing it improves processor efficiency, as the upcoming charts will demonstrate. So we're going to be looking at several charts today from IntelliMagic Vision that provide great visibility into these key systems metrics to help identify where the opportunities for efficiencies can be found. Now, this chart breaks out cycles per instruction into the productive and unproductive components that we just mentioned. The space above the blue line and below the red line on this chart reflects the cycles that are productively spent executing the instructions for your workload. And this would be the CPI value if all required data instructions were always present in level 1 cache. And it's called the estimated instruction complexity CPI because it reflects the mix of simple and complex machine instructions in your workload. Now, this may be impacted by migrations to new processor technologies that incorporate internal improvements in processor architecture, but otherwise, it's likely to be relatively constant based on workload. And again, think of this as the productive cycles from the earlier CPI slide. But since we have a limited finite amount of level 1 cache, the portion below the blue line reflects the cycles spent waiting for data to be retrieved from processor cache or memory due to level 1 cache misses, and thus it's termed the estimated finite CPI. Now, this IntelliMagic Vision chart breaks out those waiting cycles of estimated finite CPI by the various causes and estimates the relative contributions of each to the total cycles per instruction. The bottom pink band here represents additional cycles caused by delays related to dynamic address translation caused by translation look-aside buffer misses. The remaining colored bands on the chart represent the components of RNI and reflect the estimated times for accesses from each source. In this example, during the prime shift, accesses to level 3 on-chip cache, the dark blue band, and memory on-node and on-drawer, the light blue and green bands near the bottom, are the largest contributors to estimated finite CPI. Reducing RNI means reducing the unproductive cycles spent waiting for data to be fetched from processor cache and memory, which improves cycles per instruction and thus processor efficiency. And since this RNI-driven component represents about half of the overall CPI, this is the basis for the rule of thumb that Brent mentioned earlier, that a 10% reduction in RNI can be expected to result in a 5% reduction in MIPS. So reducing RNI means getting more MIPS out of a processor by improving processor cache effectiveness. So how do we make that happen? Well, to achieve that, first we need to review a little bit about HiperDispatch. HiperDispatch has been around for a long time, but it plays an even more vital role on the Z13 processor where cache performance has such a big impact. There are many aspects of HiperDispatch, but what's pertinent to our discussion today is that HiperDispatch interfaces with the Prism and ZOS dispatchers to establish affinities between units of work and logical CPs, and between logical and physical CPs. Now, this is important because it increases the likelihood of units of work being redispatched back on the same logical CP and executing on the same or nearby physical CP, thereby optimizing the effectiveness of processor cache at every level by reducing the frequency of processor cache misses and by reducing the distance into the nest required to fetch data. Now, when HiperDispatch is active, Prism assigns logical CPs as vertical highs, mediums, or lows based on LPAR weights and the number of physical CPs. Vertical high CPs have a one-to-one relationship with a physical CP. Vertical mediums have at least a 50% share of a physical CP, and vertical lows have a low share of a physical CP and are subject to being parked when not in use. And this classification into vertical high, vertical medium, and vertical low is also termed polarity. Now, having more work executing on vertical highs significantly improves cache effectiveness because that work always accesses the same level 3 cache it was using the last time it was dispatched, and usually the same level 1 and level 2 cache. On the other hand, vertical mediums and vertical lows may be dispatched on various CPs where they will be contending with workloads from other LPARs, making the likelihood of their finding the data they need in cache significantly lower. This set of IntelliMagic Vision charts uses statistics from the SMF-113 records to estimate the life of data in the various levels of processor cache, and each are graphed over a 24-hour time period. This provides another data point reinforcing the importance of reducing cross-LPAR contention for cache. So in this example, cache working set data remains in level 1 cache for less than a tenth of a millisecond, in level 2 cache for less than 2 milliseconds, and in level 3 cache around 10 milliseconds for most of the day. So by the time an LPAR gets redispatched on a CP, after another LPAR executed there for a Prism time slice of 12.5 milliseconds, its data in level 1, level 2, and level 3 caches will all be gone. And the good news is those working sets will be rebuilt from level 4 cache. But the bad news is that each access to level 4 cache may take 100 or more cycles. So this reinforces the importance of having as much work as possible executing on vertical high CPs. So as expected from this discussion, increasing the amount of work executing on vertical highs and thereby eliminating cache contention from other LPARs can significantly improve RNI. So this IntelliMagic Vision chart compares a system's RNI across 2 separate days. On the first day, the system had a vertical CP configuration of 3 vertical highs and 2 vertical mediums. On the second date, the configuration had changed to 5 vertical highs. This resulted in a 20% reduction in the RNI, which based on the earlier rule of thumb would reduce MIPS consumption by about 10%. This chart, showing RNI for the same dates and system, but now by logical CP, is very informative because it confirms that the two vertical medium CPs, CPs 6 and 8, the light blue and green lines at the top of the before chart on the left, had by far the greatest reductions in RNI. When they were running as vertical mediums, they had a significantly higher RNI than the vertical highs because they were competing for processor cache with other LPARs and their disparate workloads. So this clearly confirms that increasing the amount of work executing on vertical highs and thereby reducing the cross-LPAR contention for processor cache significantly improves RNI. Now, IntelliMagic Vision provides a number of charts that provide great visibility into the amount of work executing on vertical mediums and vertical lows, which shows then where the greatest opportunities to achieve RNI efficiencies are. So this particular chart displays the percentage of general-purpose CP time dispatched on vertical highs for these four processors over the selected time interval. The processor represented by the red line at the bottom of the chart has the lowest percentage of work executing on vertical highs, and thus it represents the largest potential opportunity to gain efficiencies. Drilling down on that processor, this chart displays the MIPS executing on each type or each polarity of logical CP over the selected time interval. The MIPS executing on vertical highs are in the bottom in yellow, on vertical mediums in blue, and vertical lows in red. And then finally, this chart provides visibility by LPAR into that same view of how much work is executing on vertical mediums and vertical lows for the time interval. In this case, the vertical mediums is work executing there is in blue, and yellow, vertical lows in yellow. So these IntelliMagic Vision charts provide various viewpoints into the amount of work executing on vertical mediums and vertical lows, giving visibility into the primary opportunities to gain efficiencies by directing more work to execute on vertical highs. So by way of review, delivered capacity on Z13s is more dependent than ever before on effective use of processor cache, which minimizes the time the processor spends unproductively waiting for data to be fetched from processor cache or memory, and that's quantified for us by the RNI metric. A primary way to reduce RNI is by increasing the amount of work executing on vertical high CPs, since that work which executes on CPs dedicated to the LPAR, is not subject to cross-LPAR contention for processor cache, as is the case for work that executes on vertical mediums and vertical lows. So reducing RNI improves processor cache efficiency, which results in consuming fewer MIPS, which translates directly into reduced MLC charges. Now, we've already seen the great visibility that IntelliMagic Vision provides to identify the processors and LPARs where there are sizable workloads not experiencing the improved cache efficiency that results from processing on vertical highs. So what are some actions we can take to increase the amount of work executing on vertical highs? So as we said earlier when discussing HiperDispatch, the number of vertical high CPs assigned to an LPAR is dependent upon two factors: the LPAR weight and the number of physical CPs on the processor. So those are the two factors that we can influence. First, we can adjust LPAR weights. The number of vertical highs on a high CPU LPAR could potentially be increased by raising the weight of the LPAR, thereby increasing the aggregate MIPS executing on vertical highs on that processor and experiencing the resulting improvement in RNI. If the characteristics of your workloads on your LPARs change between shifts, automating LPAR weight changes corresponding to those shifts may be another way to increase the MIPS executing on vertical highs. And finally, fewer larger LPARs may be a configuration option that would increase the amount of work executing on vertical highs in your environment. Second, consider options to increase the number of physical CPs. Installing additional hardware capacity may be a highly cost-effective option in which a one-time hardware acquisition expense may be very rapidly recovered by significant ongoing recurring savings in MLC software expense. This was the scenario driving the efficiency examples shown in this webinar. Another way to increase the number of physical CPs without incurring additional hardware expense is to opt for subcapacity hardware models. These processor models provide significantly more physical CPs and the associated level 1 and level 2 processor cache for the same MIPS capacity, which translates into more vertical highs. All right, we're going to have a second polling question. Brent, do you want to talk about this one?
Hand side of your screen now about the status at your site for optimizing RNI and achieving the maximum vertical high for your site. So either not started, not really aware of what the RNI metrics are at the moment or your vertical high percentages, or B, early stage, you've launched an initiative and actively exploring the area, or C, fully engaged, or D, mature. So that poll will pop up here. I think it's really an interesting topic to look in. So there we go. 65% have not yet started. So there should be some good opportunities to reduce the software bill at that or early stage. A couple are mature and 10% fully engaged. So thank you very much for doing that. Let's switch back to the slides. Okay.
All right. Thanks for your input on that. So increasing the MIPS you get from Z13 processors through system tuning changes to reduce RNI represents just one area of many that can help you achieve significant reductions in MLC software charges. There are a broad range of areas that we review in the no-cost MLC workshops that we offer as we leverage the visibility provided by IntelliMagic Vision into data from your systems. Another area of focus is LPAR software configuration. Since the entire MSU consumption of an LPAR is charged for every product that executes there, no matter how small that product's workload may be, LPARs that are configured with a reduced software stack create an opportunity to achieve savings without any reduction in MSUs. And then going along with that, LPAR workload optimization leverages that kind of a configuration that includes LPARs with reduced software stacks to ensure that work executes on the lowest cost LPAR that supports the software required by that workload, seizing every opportunity to execute work where MSUs are on sale. Since MLC charges are based on the peak 4-hour rolling average for the month, another area of optimization is to optimize the 4-hour rolling average, minimizing workload spikes that may drive an abnormally high monthly peak. Prism and ZOS support numerous types of capping, and IntelliMagic Vision provides visibility to quickly identify and size the workloads that are contributing to the monthly peaks, facilitating the ability to establish those caps in a manner that both helps optimize MLC expense while still providing the required level of service for time-critical workloads. And then finally, batch workloads often provide some flexibility in terms of their rate of execution. And the ability provided by IntelliMagic Vision to quickly identify the size of the batch workload executing during any interval and to drill down into the components of that batch by system, service class, report class, or job name provides a visibility needed to identify opportunities to minimize the contribution of batch to monthly peak 4-hour rolling averages and thus MLC charges. So those potential areas of MLC reduction we just discussed, along with a couple of others, all played significant roles in the 3+ year MLC expense reduction journey that I led at my previous employer. This chart displays the actual percent expense savings during that period in green from the starting point versus the business as usual case in red. Now, when factoring in business transaction growth and IBM MLC price increases and adjusting for a new technology hardware discount, if no actions had been taken, the MLC charges would have been expected to increase by 59%. But as a result of all these actions, a cumulative actual expense savings of 33% was achieved, demonstrating that opportunities for reducing MLC software charges can be very significant. All right, now we're going to transition into a live demo. All right. A number of new capabilities and reports have been introduced in IntelliMagic Vision version 8.8, which becomes generally available next month, to provide visibility into the key processor metrics that help facilitate the types of MLC analysis and RNI tuning that we've been discussing in this webinar. And several of these appear under the processor reporting focal point and in the 4-hour rolling average and capping report set. So this first report shows visibility into 4-hour rolling average by processor. And from here, we can drill down by system and to see what's the contribution of each system to the 4-hour rolling average on that processor. Now, we could continue to operate at that system level, or I'm going to just go back up to the KEC level and operate from there. Now we can drill down here and see the actual consumption of CPU per RMF interval and see how that drives increases in the 4-hour rolling average. So the blue line is the actual consumption in whatever your RMF interval you have defined, and the 4-hour rolling average is in red here. Now, from here, we can drill down by workload and say, okay, what workload is driving the CPU use at this particular point in time? And we see all the contributing workloads. Now, perhaps this is more batch than we are normally accustomed to seeing contributing to a peak 4-hour rolling average. So we want to drill down into that batch and see what systems it was coming from, and almost all of it during that peak period was coming from this system, H016. And let's say, well, we'd like to see what service class is generating that work, and so we can drill down there, and here we see what service class is, and then we could also drill down further into address space names. So IntelliMagic Vision gives us great visibility to quickly determine the workload elements that are contributing to the peak 4-hour rolling average for the selected interval that we're examining. Now, if we're utilizing WLM capping, seeking to manage spikes in the 4-hour rolling average, this chart provides visibility into the duration of when WLM capping was in effect for each system. Now we'll demonstrate some of the key charts that were also referenced in the presentation that help direct us where to start with efforts to improve processor cache efficiency. So this chart provides visibility into the percent of CPU that's executing on vertical highs for each processor. So lower percentages here represent greater opportunities to improve cache efficiency. So let's drill down into MIPS by polarity for this processor A here. And here we see then how much the MIPS that are being consumed throughout this day or across the time interval, and the amount that was executing on vertical highs here in gold, and vertical mediums in blue, and vertical lows in red. And this report provides an LPAR view into similar data. The MIPS by polarity, with the MIPS executing on vertical highs in red, vertical mediums in blue, and vertical lows in yellow. Again, pointing to where are the primary opportunities for processor cache efficiencies. Now let's look at the visibility that IntelliMagic Vision provides into relative nest intensity for a set of systems. As we discussed earlier, RNI is a primary metric that measures the delay a workload experiences waiting on data and instructions to be fetched from the cache and memory hierarchy so they can be executed. So improving RNI improves processor performance. So let's zero in on one system here. So here we see the RNI for this particular system. Now in this environment, a hardware change was implemented to increase the number of vertical highs available to this system. So I'm going to change the date interval here to advance to that date when that change had been implemented. So here's the RNI after the change. Now, of course, you probably don't have a photographic memory like I don't to remember exactly what it was like before. So IntelliMagic Vision makes it very simple to compare time intervals to identify the impact of a change. So here we see that this change reduced RNI by over 20% on this system, which again, going by our rule of thumb, would mean 10% reduction in MIPS. Now, we spoke in the presentation about how much more efficient work is when it executes on vertical highs because it avoids contention for processor cache from other LPARs. So this chart, which is a drill down of RNI now by logical processor, substantiates that. Again, at the time of the before chart on the left, the vertical CP configuration for this system was 3 vertical highs and 2 vertical mediums. Notice how much higher the RNIs were for these 2 vertical mediums, CP 6 and 8, the light blue and green lines at the top of the before chart on the left, how much higher that is than the 3 vertical highs below, reflecting the impact of cross-LPAR contention for cache. Now, at the time of the after chart on the right, the vertical CP configuration had changed to 5 vertical highs. And note the magnitude of the reduction for those CP 6 and 8 that used to be vertical mediums and are now vertical highs. And this was the primary factor driving the 20+% reduction in overall RNI for this system. All right, so this concludes my demo, and I'm now going to hand it back over to Brent.
Okay, MLC Workshop. I'm going to wrap up our time today. There should be a couple of minutes for questions just at the end, but I wanted to let you know about how you can access Todd's expertise to help you understand where you're at, along with IntelliMagic Vision. Basically, we will help you identify unrealized MLC reduction opportunities at your site. The process is to use what we call RMF Pack to collect the records that we need along with your SCRT files to send to us, and we will analyze that. Todd will be involved in that, so some free consulting. The cost for this is no charge if you're in North America at this point. And we do it actually using our software as a service platform, and the objective, of course, is to help you really just understand what's the potential for reducing cost at your site. It's a pretty quick and easy process. It takes somebody, maybe half a day to get the instructions on how to pack up the data and FTP that to us. And then we'll load it into the software as a service platform, do our analysis, prepare a presentation, and then present it to your team, and then actually give you some access to the interactive interface on the software as a service platform. So it turns out this software as a service is actually a pretty good fit for this problem about processing the SMF data. There's no personal information in the data, so security is usually okay with sending these metrics about the infrastructure performance off to a SaaS provider like us, and then it gives us the opportunity to easily see what's going on and provide some advice. So our customers that engage with us on this platform typically also engage some professional services hours on a monthly basis to have somebody to help advise them and accelerate the process for optimization, or to help them when certain performance situations come up, because this is pretty much all we do, looking at this kind of data for customers. And some of the largest mainframe shops in the country are actually doing this on a daily basis, sending us data. So at this point, I think that's all of the content that we had. Janine, do we have some questions that
we do, Brent. We have quite a few. So I just want to tell our attendees, please continue to submit your questions in the Q&A panel. If we don't get to them all today, someone will follow up with you via email. Okay, first one. I assume you would wish to negotiate your CEC-based software licenses as consumption-based, correct?
Yes, this is Todd. Yes, that's exactly correct. That's a very perceptive question. Yes, for other independent software vendors to take advantage of this where you're utilizing additional hardware capacity to save on your MSU-based software, you want to change those contracts over to be usage-based or MSU-based as opposed to hardware capacity-based also. Yes.
Okay.
And I might just throw in as well that we do have some experience in advising some customers with different software vendors of which vendors were willing to make some changes in the licensing structure and so on. So another area of value.
Okay. If our RNI is already below the 1.0 threshold IBM defines for high workloads, is there still any benefit to seeking to reduce further?
Yes. Any reduction that we talked about today, any reduction in RNI will make the processor, you'll get more capacity out of your processor and result in a lower MIPS consumption. So that's an important concept to realize that just because an RNI is not extremely high to begin with, that doesn't mean there isn't an potential opportunity for improvement.
Okay. Here's a good one. You said one way to increase the amount of work executing on vertical highs is to add hardware capacity, which costs money. Doesn't that offset the savings from the MLC reduction? Cost
benefit analysis would certainly need to be done. The experience that I've seen is that the magnitude of the savings and the fact that the hardware acquisition is a one-time expense and the MLC savings are recurring year over year has made that a very compelling thing to study.
Okay. Are these concepts also applicable to other platforms like the EC12?
Yes. The reason we focused on the Z13s today is because of that dynamic that Brent talked about at the beginning, that in the past when you went from one generation processor to the next, the cycle speeds were always getting faster. So, all boats were lifted by the rising tide, right? And so, some workloads might have gotten more benefit, some less, but, everybody performed better. What changed between the ZC12 and Z13 is that the cycle time actually got slower, but because of the improvements in processor cache processing, the rating of the processor went up. So that's why processor cache has become much more critical to be aware of with Z13s and can have a much bigger impact. But the concepts of reducing RNI to save and reduce MIPS consumption, MSU consumption, is applicable, yes, to all ZOS systems.
Okay, that kind of covers this one, but I just want to make sure. So it would also apply to ZVM or ZLinux?
No. The concepts discussed today are ZOS specific. And
okay.
Yeah.
Good to clarify. Is there any correlation between size of the mainframe and the RNI optimization potential?
There can be opportunities in sites of any size. Smaller sites that maybe have a limited amount of LPARs, there may be some aspects of an MLC reduction process that may not be applicable in a smaller environment. So we think there's opportunities across the board, but the size of the opportunities may vary depending on the size of the installation.
Okay. Well, that is all we have time for today. I want to thank everyone for attending today's webinar, and I especially want to thank Brent and Todd for sharing their expertise with us today. We will be sending a follow-up email with a link to the recorded webinar to anyone who registered for the event. That concludes our webinar. Thanks again, and have a great day.